Hello. In this video, we want to look at slope, the slope between 2 points on a line. We want to take that formula for slope and use it to develop the distance formula, the formula for the equation of a circle, and the midpoint formula. We start with an xy axis. I'm working here in the first quadrant, and I'll identify 2 points. Point and the second point. We'll call this point x1, y1, and this point will be x2, y2. And we'll talk about the segment connecting these 2 points. And I'm interested in finding the slope of this line. Now we know that slope is the change in y divided by the change in x. So, looking at this point, from x1, I come over to x2. From x2, I come up here from y1 to y2. So this distance from x1 to x2 is x2 minus x1. And the distance from y1 to y2 is y2 minus y1. This distance is the change in x. This distance is the change in y. And so I can express the slope as y2 minus y1 over x2 minus x1. That's my formula for slope. Now, with that formula, I can say, well, I've got a right triangle here because I've got a right angle. The Pythagorean theorem tells me that the sum of the squares of the 2 legs is equal to the square of the hypotenuse. So here's my hypotenuse. I'm going to call that r. So by the Pythagorean theorem then, I have that the leg x1 minus x2 squared plus y2 minus y1 squared equals r squared. The sum of the squares of the 2 legs is equal to the square of the hypotenuse. Now, r is the distance from this point, x1, y1, to this point, x2, y2. If I want to know what r is, I can simply take the square root of both sides of this equation. So on the left-hand side, the square root of x1 minus x2 squared plus y2 minus y1 squared would equal r. That's the distance then between the 2 points. Now, suppose I take a string, and suppose I hold the string at this point, stretch it to r, and draw a circle. We remember a circle is the set of all points in a plane that are equidistant from a fixed point. The fixed point is the center of the circle. We'll label that point HK. The distance that each point is from the center is the radius of the circle. And that we will label as r. So you see what I'm having then? This formula, if you will, this formula from the Pythagorean theorem gives us the equation of a circle whose center, let's say, is at x1, y1. And this should be x2 minus x1 to be consistent. So if I replace x1, y1 with hk, I have x2 minus h squared plus y2 minus k squared equals r squared. That's the equation of a circle. Now, since xy is a point on the circle, I do not need the subscripts, and I can simplify that to x minus h squared plus y minus k squared, and that is the equation of a circle right here. So from our definition for slope of a line, we move from this to writing slope as change in y over change in x. We then apply the Pythagorean theorem, and the sum of the squares of the two legs is equal to the square of the hypotenuse. Well, that said, I can take the square root of both sides and I get the distance formula. Remembering what a circle is, the center is the fixed point hk, the radius is r, and I have the equation of a circle. All of these details are coming from these 2 points. Okay? So let me erase this. And now let's look at these points again. But now I want to look at these points in terms of function notation. So I'm going to make a few changes. This will still be x1, this will still be x2. But I'm going to call this axis not the y-axis, but the f of x axis. And then if you remember your function notation, if this point is x sub 1, this point would be f of x sub 1. And if this is x sub 2, this point would be f of x sub 2. Making this distance here f of x sub 2 minus f of x sub 1. So then I could express slope as f of x sub 2 minus f of x sub 1 divided by x sub 2 minus x sub 1. Now this will give us a very powerful development. So I'm going to write my slope as f of x sub 2 minus f of x sub 1 divided by x sub 2 minus x sub 1. Now I want to change this a bit. Suppose we say this. Suppose I want to identify this starting point as x, and I want to identify the distance to a second point, say that is h. So instead of using x sub 1 and x sub 2, I'm now going to use x and h. So this point would just be x. And then this point, watch this point will become x plus h. Now look how that will change with the function notation. This will be f of x. This point now will be f of x plus h. Look at the implication in my formula for slope. And it will be f of x plus h minus f of x divided by x plus h minus x. Again, I'm looking at the distance, okay? This is f of x plus h minus f of x. This is x plus h minus x. Take a look at your denominator. X plus h minus x. The x's drop out. And I'm left then with just h. Now your book, and most books, will call this expression the difference quotient. And it is the key to the basis of differential calculus. In calculus, we want to be able to find instantaneous rate of change. I want to be able to find the slope of a line when I only have one point. You say, well, how can you do that? Very simple. You see, if I have a point x and a distance h that is so microscopically tiny that these 2 points are essentially one and the same, then that's going to give me instantaneous velocity. And so if I take this difference quotient, which is nothing more than our formula for slope, and I let this distance h shrink to essentially 0, this formula, which would give me the slope of a line between 2 points, is in essence giving me the slope of a line at 1 point. This is very powerful stuff. And from this simple definition for slope, we now have the explanation and a formula for differential calculus. In the next video, we'll look at an example.